right, as we finish our test review, want to quickly review graphing linear equations. Remember, a linear equation, Noah, is an equation that is graphed as a line, hence the word line, r, linear. And with our linear equations, we wanted to get them in what's called slope-intercept form. Brecken, what is slope-intercept form? All right, y equals mx plus b, where the m, Maddie, represents... It is a fraction. It's specifically rise over run, in fact. We call it slope, hence the name slope. And then, of course, Brecken, the b, represents the y-intercept, hence slope-intercept form. And the key, again, is to get slope-intercept form as we work with our equations. So, for instance, if I have the equation 2x negative y equals 7, well, that's not in slope-intercept form. Noah, what might I do to get that equation into slope-intercept form? Remember, the key to slope-intercept form is y by itself. We could do a double swap, and that would give us, and we could either say equals y, or we could say y equals. Really doesn't matter. I could also put the 2 over 1, so that I can see, class, that the y-intercept is negative 7, and the slope is 2, or 2 over 1. So remember, for actual graphing, we start by plotting the y-intercept. So we'd start at the negative 7. And then from there, class, we would rise 2 and run forward 1. And we just use our straight edge to connect the dots. I would recommend having a straight edge available for the exam. So what about this one? 3x positive 5y is equal to 10. How would we get that into slope-intercept form, Brecken? Okay, to get well, it's a positive, but we're moving it over so it becomes, yeah, remember when it changes sides, it changes signs. All right, and then, good, to get, good, or 3/5 x, so either one is fine. There we go. So for this particular equation, Maddie, we would start by positive 2 for our y-intercept, plotting that there, and then, good, left or backward 5. 1, 2, 3, 4, 5, and we would connect the dots, and there's our equation there. All right, questions on graphing. We remember learning this. Okay, coming back to us now. In general, solving equations, there's all different kinds of equations we learned this year. Some of them very basic, like, for instance, go and get some paper out if you don't already have it available. Equations like this. You know, we would start by doing what with this particular problem? Brecken? Right, remember, we always want to get rid of the parentheses first, and that generally means distributing, or sometimes foiling, or maybe even squaring a binomial or something. In this case, distribution. And what do we write for our next line on this equation? There we go. Once we've gotten rid of parentheses, Maddie, then what do we need to do? The combine like terms, and I do have some like terms here. Now, there's nothing like to the 12 over here, and for the 3x, there's nothing, well, really anything with it, period, but certainly nothing like on the other side. But the 5x and negative 6x combine to give us, go to negative x. Negative 12 is equal to 3x. Noah, now what will we need to do? Brecken? I've got an x on both sides. That's, you can't have that. So something's got to go. Right, we always want to get rid of the little one, remember. So thinking Emma. Just kidding. We always want to get rid of the little one. And the little x is the negative x, so we'll bring it over as a positive x, and that'll give me. And once the x is, the x term is over there, now we just worry about getting it by itself, which is one easy step, Noah. Right, divide away the 4 to get x equals -3. Okay, so we've been doing equations like this since the beginning of the year. Another type of equation that we worked on this year were rational equations. That is, equations with fractions. And we said if you have fractions in equations, you should hate them. I tried to brainwash you into that. I don't know how effective I was. You might have been sleepy that day. But we hate these fractions, so we're going to get rid of them. And class, what do I do to eliminate fractions from my equation? Oh no. Multiply everything by the LCD. So even if I had like a +2, that's not a fraction. That gets multiplied by the LCD as well. What is the LCD here, class? 12. So everything gets, well, if this were there, it would get multiplied by 12 too, would give us a 24. But everything gets multiplied by the 12. And the reason we multiply by the LCD is that the LCD will do what with each and every denominator, class? Cancel. That's the whole point. Get rid of fractions. We've got to cancel that denominator away. So here we cancel, class, to get a 4. Here cancel to get 3. These cancel cleanly. 1 technically. Here cancel to get 2. And so what's my equation going to look like now, Noah? Ooh, careful. All right, and then once again, what do we got to do now, Brecken? Combine like terms to get is equal to 5 negative 2x. Now, Noah, what do I need to do now? Get rid of the little x. Which one's the little x? The negative 2x is actually the smaller one. We're going to move it over, Maddie. It'll become to get x equals 5. And there we go. Questions on that? We did have one special type of equation involving fractions, and that was an equation in which it was simply one fraction equal to one fraction. And if you have a single fraction equal to a single fraction, class, we call that a proportion. And how do we solve proportions, class? Cross multiply. So that the product of the means will equal the product of the extremes. What do we get when we cross multiply? Maddie? Good. And then from here we solve it like we would any other equation. Brecken, now we need to good. Bring the 12x over as a negative, getting rid of the little x. And at the same time, let's go ahead and move the, well, if I'm bringing the x to the left, I want to send the non-x's to the right. Let's move the 8 over instead as a, and so we combine over here, class, to get 4x is equal to negative 4. Good, so our answer will be x equals negative 1. Any questions on that? All right, another type of equation that we talked about involved absolute value. And the key to absolute value, class, is to remember 2 words. Positive, negative. Remember, the whole premise of absolute value is it doesn't matter if it's a positive in there or a negative in there, it's going to come out the same. So absolute value of positive 3, absolute value of negative 3 is the same either way. So the key to absolute value then is to get the absolute value set equal to positive negative. So if I had this equation, 2 times the absolute value of x plus 3 minus 9 is equal to 11, what would we need to do here? Let's start with Noah. Good, we want to start by treating this whole absolute value thing as kind of like our variable. So we want to get it by itself, so we're going to move the 9 over as a positive, and that'll give us 20. Then we will want to, reckon, divide away the 2. Remember, we don't distribute into an absolute value. We get rid of the coefficient, divide by 2 on both sides. And now my absolute value of x plus 3 is isolated, and it's going to be equal to 10. Here's where we split one equation into 2. Maddie, what are my 2 equations? Good. The x plus 3 equals 10, really straightforward, but also the x plus 3 could equal negative 10. We set it equal to positive and negative. And then for each of these, to get the x by itself, we have to just move the 3's over class as negative 3's. And when we do, we get what? 2 answers, Noah? We had 7 and negative 13 questions on absolute value equations. All right, another type of equation we talked about involves an x squared in the equation. And we said anytime there's an x squared in the equation is considered to be a, starts with a Q, quadratic equation. And we said a quadratic equation is going to have how many answers, class? 2. But the key to the absolute value equation, or the absolute value, that's a lot. Rewind. The key to a quadratic equation is to set the whole equation equal to 0. Now, whatever side the x squared is on, assuming it's positive, that's not the side that's going to be 0. So we want to make this side 0, but it isn't 0, it's 18x. How could I make it become 0, Maddie? Yeah, just move it out of there. If we move it out, there's nothing left, and nothing is expressed mathematically as 0. And Maddie read it as x squared negative 18x positive 32. Maddie, why did you put the 18x in the middle? Why not at the end or at the beginning? We want descending order so that our next step falls naturally. What do we do once we've set the whole equation equal to 0? Noah? The same thing we do every time. What do we do all the time in this class, it feels like? When in doubt, class, factor. When in doubt, factor. And that's what we're going to do here. So we're going to set the whole equation equal to 0, Noah, and then we're going to factor. How would I factor this, Noah, for redemption? Good. 4 and 8 would be our first thought, but that doesn't give you an 18, does it? 1 and 32, of course, wouldn't give you an 18, but 16 and 2 would. Once we've done that, we're going to take each of these factors. Kind of like absolute value becomes 2 equations, we're going to split this into 2 separate equations, and each factor individually, class, we will set equal to 0. So that x minus 16 equals 0. So that x minus 2 equals 0. Now, oftentimes, I don't actually write this off to the side. I do this step mentally, or perhaps put a little equals 0 like that. But that's really what we're doing, is 2 separate equations. Well, if x minus 16 equals 0, class, then x is equal to 16. And if x minus 2 is equal to 0, then x is also equal to, or could also be equal to, 2. And we said for our purposes, it will be both of them, both 16 and 2, though oftentimes we'll write the word or. 16 and 2 are answers questions on quadratic equations. We just looked at several different types of equations you'll see on the exam here in just a little bit. Does anyone want to see another one of these types of equations, or do we feel like we're good to go? All right, kind of along the same note as equations, we talked about a set of 2 equations that we could solve together for not just x, but say x and y, solving for 2 unknowns. What do we call that set of 2 equations, class? A system of equations. We've been working with those nonstop for the past several months. People watching on YouTube are like, what is wrong with this class? I don't know either. You tell me. Go and write down this system on your paper. Work it with me. 3x minus 2y is equal to 14, and 5y is equal to x minus 22. Let's go and take a look at this system together. Now, there's 2 ways in which we can solve a system. Maddie, what are our 2 methods? Good, either the addition method or the substitution method. If I want to use the substitution method, what's the key, anyone? Good, get a letter by itself, get a variable by itself. I don't have that right now, though it wouldn't be too hard to get a variable by itself, right? If I want to use the addition method, what's the key, class? Line everything up, x, y equals number. They're all like, we're just going to let Brecken answer everything today. You know what? Thank you, Brecken. I appreciate it. So, Noah, you keep silence. What do you want to do? Addition or substitution? You got to pick one. Substitution, all right. So that means you want to get a letter by itself. What letter? The x? No, the other x, right? You want to get the x by itself, and that's pretty easy if you just move the as a. So we end up with 5y plus 22 is going to be equal to the x. All right, so we've got a letter by itself. Now what? Plug it in, plug what in? Good, plug the 5y plus 22 in for the, right here? No, the other x, of course, the other equation. And we put it in right here so that my top equation now reads what? There we go. And I don't mind if you were to do the distribution in your head, though for sake of showing it on the board, I appreciate you not doing that. Let's go ahead and distribute now. Minus the 2y is equal to 14. We can combine the 15y and negative 2y, class. 13y. And at the same time, let's get the 66 over here as a negative 66, which gives us what? Negative 52. Remember, keep the sign of the greater absolute value so that y is equal to negative 4 when we divide away the 13. So that's half of my answer. But remember, we don't want to stop with just one value. We need to go back and get the other. What are we going to do to find the x value here, Brecken? And that'll give us, of course, negative 20 plus 22, which equals 2. And so there's our answer questions on systems of equations. Should be good with these. We've done a lot with them. All right, we've worked a lot recently with exponents and radicals and things like that. Want to make sure we're good. In fact, our last test covered this, so this should be relatively fresh information, but could use a little bit of refresher here just to make sure we're geared up, since we've reviewed a lot of more long-term concepts here of late. If I had something like negative 4 m squared x cubed, and I were cubing it, 3 steps, sign, number, letter, what would I get, Maddie? Good, negative 64, m to the 6x to the 9th. Remember, negative to an odd power, it's negative. If it had been an even power, it would have changed to a positive. 4 cubed, 4 times 4 times 4 is 64. And then class, when you raise a power to a power, you multiply the exponents. So, if I had a 15, a to the x, b to the 7th squared, what would I get for my answer? Noah? Ooh, 15 squared should be memorized. You're going to have a hard time next year if it's not. And the year after. And the year after. Class, 225. I pray continue. No. There we go. 225, a to the 2x, b to the 14th. Don't let the literal exponent throw you off. Noah did. Just multiply. X times 2 is 2x. And go from there. If we were to take the root, we'll follow the same basic steps. If we wanted, for instance, the square root of 289, x to the 16th, y to the 4th. Well, sign, number, letter. Good thing it's positive, because can you take the even root of a negative, class? No, that'd be imaginary. But I can take the square root of a positive, of course. Now, technically, we get positive, negative. Principal root, we just assume positive. What is the square root of 289, class? $17. I should have quizzed you guys like 5 more times. All right, and then when we take the root, which is an understood 2 of powers, We divide divide exponent by index to get x to the 8th and y squared. You did it.
I knew it.
All right, what if I had the cube root of negative 125? R to the 9th, S to the 6m. What would we get for our answer here, Maddie? Ooh, dividing 2m. There we go. Odd roots keep their signs. Cube root of 125, of course, 5. Cube root of that, of course, r cubed, 9 divided by 3, and then 6m divided by 3 gives us the 2m. Okay, so some problems are going to be very easy like this. The basic, raising to a power, taking rational roots. But there, of course, are irrational roots as well. And that's really where we spent the majority of our time in the last chapter, was working with these irrational roots. For instance, the square root of 49 is rational, but the square root of 48 isn't. What would I do with a problem like the square root of 48, bracket? Right, we'd factor 12 times 4, for instance, so that, no, I can't take the square root of 48, but I can take the square root of 4 at least, which is a factor to get. So I get 2 times the square root of 12. But I'm not done yet, because right, I can factor that into 4 times 3, where again I can take the square root of 4, and that gives me another 2 times the 2 that was already here. Good. Perhaps better had we said 16 times 3, but if we didn't know our 16 times tables, not a problem as long as you stick with it till you get it fully reduced. If we had the square root of 3 sevenths, ooh, not allowed to have class A irrational denominator. And right now, because the 7 is inside the square root, the denominator is irrational. What are we going to do here, Maddie? Good. Technically, it's square root of 7, but it's all under the radical, right? So that my fraction changes from 3 sevenths to, and then we get, good. The square root of 21 you can't do nothing with, you just leave it, but the square root of 49 becomes a rational 7, a rational denominator. If we had a big index, not square root, cube root, which is what we're used to seeing, but like a 6th root, what would I need to do here, Noah? Good, we want to make this smaller, but the key is to rewrite everything as a power. So the x to the 4th is already a power, but 49 wasn't. So we rewrite it as 7 squared, as Noah said, and then we can reduce what? There we go. Take a 2 out of the index and all the exponents, and we end up with the cube root of 7x squared. Remember, in order to add radicals, class, they have to be similar. And right now, are these similar radicals? No. So remember, for addition of radicals, you've got to reduce them first. Get them similar. And my suggestion was, start with the easy radical. Which of these is the easiest radical, class? What? 24, because we should be able to see that that factors into. Oh, it does, but can you take the square root of 12 or 2? No. Gotta think squares. 4 times 6. Now that'll help, because I can take the square root of to get a, which means this whole thing is going to turn into, and if this turns into a square root of 6, class, there's a really good chance that this also becomes a square root of 6. Maybe. Well, let's see. Can you divide 150 by 6? If so, what do you get? 25. Hey, perfect. I can take the square root of 25. What does this become, bracket? Good. Good. And, well, maybe we got 3 for 3. Maybe there's a 6 here. Maybe. Can you divide 96 by 6? If so, what would you get? 16. Ah, there we go. So, no, we can take to get, Hey, there we go. And now we can work the problem through, and what do we get when we add? 5 times the square root of 6. If I had, for instance, 3 times the square root of 5 times the square root of 10. These are not similar radicals. But remember, to multiply, they don't have to be similar. All you need to multiply, class, is the same index. And they have the same index. So I just multiply. And what do I get, Maddie? And, but I don't want to leave the answer this way, right? Here we reduce at the beginning. Multiplication you reduce at the end. How would I reduce the square root of the 50? Factor it into 25 times 2 so that you can pull out a from the 25 to get. And there's our answer to that. Of course, if we had a 2-term radical denominator, class, we would need to rationalize it by multiplying by the conjugate of the denominator. We just were working on that recently. Does anyone need to practice rationalizing a 2-term radical denominator? What about a monomial denominator? Well, then, remember, you just multiply by whatever it takes to get a rational root, and then take the root. Does anyone want to practice rationalizing denominators with monomial radicals in the denominator? We all feel good with rationalizing. I know it was what we just did a few days ago. I just want to make sure we're all still good. I got about 3 more minutes. Let me do a last run through the test, make sure that we have reviewed everything you need. Anything to the 0 power, class? Equals 1. For a fractional exponent always indicates a root. But which part of the fraction, numerator, denominator, is the root? The denominator of the fractional exponent. The numerator is your power. Yeah, I remember this now. Remember when we talked about graphing linear equations? We talked about the idea that linear equations could be parallel to each other. They could be perpendicular to each other, or they could just be intersecting. They could be neither of these things. What does it take for lines, linear equations, to be parallel? Same slope. Now, again, the way you learned it last year was they never intersect, but of course that means they have to slant the same, or they have to have the same slope. Remember, M means slope. What about perpendicular lines? Obviously, we know they make right angles with each other, but what does it take for lines to be perpendicular? But what does it take to be opposite? For instance, if the slope of this line is, I don't know, 3/4, then a perpendicular line would have to have a slope of -4/3. The signs are opposite and the rises and runs are opposite. We would say that they have to have negative reciprocal slopes. Negative reciprocal slopes. Now, if the slopes aren't the same, then they're not parallel. And if they're not negative reciprocal slopes, then they're not perpendicular, they just be random intersecting lines. In the Cartesian plane, what do we call these two lines that are perpendicular to each other? Axes. Remember, the horizontal axis is the x-axis, the vertical axis is the y-axis. There are 4 sections here called quadrants. Which one is this? Quadrant 3. What about this one? That's quadrant 1. This would be 2. This would be 4, and so forth. So if I gave you a random point, 7, -4, what quadrant would that be in? The 4th quadrant, because you would go forward 7 in the x and down 4 in the y. This x value, by the way, is called the abscissa. The y value is called the ordinate. We put them together to get the points. Coordinates. What do we call this place where the axes cross? The origin. Good. And if I were to draw a linear equation, we said that this point right here where the line crosses the y-axis is called the y-intercept, and then up here would be our x-intercept. Negative exponent. What does a negative exponent mean? For instance, if I had m to the negative third, what is that? Go back a little while. Negative exponent means reciprocal. So that m to the negative third class would be equal to what? The reciprocal of m cubed. What would be the reciprocal of m cubed? 1 over m cubed. What would be x to the negative second? X squared. What would be 1 over r to the negative fifth? R to the fifth over 1, or we could just say r to the fifth, right? What if I had an m cubed n to the negative fourth? How could I rewrite that, Maddie? Well, there's no real reason to move the m cubed, right? This is m cubed over 1, this is n to the fourth over 1. This is the only one I need to take the reciprocal of, right? This would become m cubed over 1, and this is where I need the reciprocal. So you're right about the 1 over n to the fourth. And then when I multiply those, I just get... Right, so remember I said that if you've got a polynomial, a negative exponent, kind of you could say means move it. If it's up, move it down. But if I had, for instance, an r squared z to the negative first over a to the negative third, well, anything that has a negative exponent we would want to move, Noah. What would I get? Brecken, help him. Well, I don't want to move the r squared though. It doesn't have a negative exponent. Let's leave the r squared up here. Right, we'll move that one down. So we move the z to the first down, that should become positive. Move the a to the negative third up to become a cubed, but let's just leave the r squared where it is. Okay, so it's been a little while apparently. Since we worked with negative exponents, we'll work more with those next school year. And I think that means we've reviewed everything on the exam. All right, we'll take a break and then we'll come right back and take the exam.